Hello and welcome to a playthrough of expectation maximization as policy improvement. We are not looking at a specific paper today, but instead we are looking at the previously explored 6 papers: maximum a posteriori policy optimization, MPO, and its cousin V-MPO, advantage weighted regression, AWR, and its cousin direct advantage regression, DAR, and also ReST-EM and VIREL. Each of them alternate between an E-step that produces a target distribution over actions and an M-step that projects that target onto a parametric policy by weighted maximum likelihood. What changes from one paper to the other are elements such as how the temperature is obtained, how the trust region is enforced, and whether E-step is solved in closed form or replaced by a filter, and whether the inference object is the policy or the action value function. MPO uses a two-step EM with a closed-form non-parametric E-step and a decoupled Gaussian M-step. V-MPO collapses both into one Adam step with stop gradient. AWR uses two regressions and a fixed temperature. DAR takes us into language model alignment with a second KL penalty against a reference policy. ReST-EM removes the trust region under binary rewards and replaces it with a base model reset between each iteration. And VIREL zooms out and reframes the space as variational inference on the action value function, with the temperature resulting from the Bellman residual. For our preliminaries here, Markov decision process is this tuple. The state space S and the action space A can be discrete or continuous. The transition kernel P is Markovian by construction. The next state depends on the current state and action and not on the history. The reward R is a real valued bounded function that takes as input state and action. The discount factor between 0 and 1 makes infinite horizon returns finite, and the initial distribution P0 of S generates starting states. A stochastic policy pi assigns a probability to each action at each state. And we have our trajectories of state, action, and so on, with the state sampled, first one sampled from the P0 position, and then the action from the policy given the state, and so on, with discount return R being the sum of the discount to the power of t times the reward. The standard reinforcement learning objective is the expected discounted return. The state action value function Q is the expected discount return starting from state S action A and following pi thereafter. So the state value V is its expectation under the policy, and the advantage is the difference between these two. The advantage has zero expectation under pi at every state. The choice between Q and A is the choice between an unbounded positive score and a mean zero score, and it helps us determine how the softmax in the E step normalizes. So Q pushes mass on the positive tail. A requires a filter or a baseline to avoid flattening towards the uniform. For Bellman operators, the Bellman expectation operator for a policy pi acts on Q functions by this definition of reward plus the discount times the expectation over Q. And Q is the unique fixed point of T. The optimal Bellman operator replaces the policy expectation with a hard maximum with fixed point Q star. The discounted state distribution under pi is this D here, where pi for where the st equal s is the marginal probability of being at a state s at a time t. The expected discounted return rewrites as state action expectation under D, and we have this objective of 1 over 1 minus the discount, and then the expectation with S sampled from D, A from pi over the reward. The callback liberal divergence from Q to P is as defined here, always greater than 0. First, we have this non-negativity, so Gibbs inequality derived from Jensen's inequality applied to the concave logarithm with equality if and only if Q equal P almost everywhere. This is what allows us to have KL penalty as a trust region. Secondary property of the KL is that it's asymmetric and that it is not a metric because it does not satisfy the triangle inequality. It has information theoretic properties as the expected number of extra information per sample if you include the data, if you encode the data drawn from Q using a code optimal for P. So the asymmetry of KL gives us two different directions, and sometimes algorithms use both. The reverse KL is mode seeking. The expectation is taken under Q. Q pays a penalty only where it itself places mass. Q can ignore regions of P that it does not cover. Minimizing reverse KL produces a Q that concentrates on the highest probability region of P and drops the rest. This is correct behavior when we want Q to pick out the best actions under a target distribution. The forward KL, P to Q, is moment matching instead of mode seeking. So for forward KL, moment matching, the expectation is under P, so Q pays a penalty everywhere Q places mass. Q cannot drop modes of P without incurring cost. Minimizing forward KL produces a Q that is at least as broad as P, and this is the behavior we want when we want a new policy to fit weighted samples without collapsing its entropy. The E-step uses reverse KL. It concentrates the variational distribution on the highest advantage actions and ignores the rest. And the M-step uses forward KL, which forces the parametric policy to stay broad against the previous policy and not collapse to a spike and preserve entropy. That dual usage is what gives this expectation maximization, exploration preserving properties without, again, explicit entropy bonus. The differential entropy quantifies for a continuous distribution, quantifies the spread of the distribution with maximum at uniform on bounded support and a minimum at Dirac. KL divergence and entropy are linked through the identity divergence of Q to P is the negative entropy of Q minus the expectation of over Q on log P, which is what separates the elbow into a log partition term, a KL term, and a state entropy term in the VIREL derivation. The Merstall maximum entropy objective adds a per step log pi at action T given ST to the reward. VIREL avoids that and lets entropy come in through the variational posterior. Jensen's inequality states that for a concave function f and a random variable x, we have this property, f of the expectation over that random variable is greater than or equal to the expectation over f of that random variable, or if and only if x is a constant or f is affine. So applied to log concave on the positive reals, it moves the logarithm inside an expectation and produces a lower bound on intractable log marginals. For any joint density pi theta x z over an observation x and a latent z, and any variational density q of z with the same support, the log marginal decomposes in the way we see here. The first term is the evidence lower bound, the elbow. The second is the KL gap between the variational q and the true posterior pi theta z given x. Because KL is now negative, the elbow is a lower bound on the log evidence, and the bound is tight when q equals the true posterior. Now, what is expectation maximization? It's coordinate ascent on the elbow. We hold theta fixed and optimize over q, and that's the E step. That sets the variational posterior to the true posterior and drives the KL gap to 0. We then freeze q instead as fixed and optimize over theta, which is the M step. Because each step is a maximization, the elbow is non-decreasing. Because the bound is tight at the start of each E step, the same monotonicity transfers to the log evidence. And that's a property that MPO benefits from. Control as inference reduces RL to probabilistic inference by introducing a binary optimality variable O at each step with likelihood proportional to the exponential of the reward. A high reward action becomes likely to be optimal action. A low reward action becomes unlikely. The temperature alpha controls how sharply that likelihood is. Small pushes the inference posterior towards the greedy policy. Large alpha flattens it towards the prior. The likelihood that every step of a trajectory is optimal is this expression of probability of O being 1 given the parameters proportional to the expectation over the exponential of the sum of the reward over alpha. And it's what MPO maximizes in its MAP. V-MPO uses similar idea, but with binary improvement variable, as we shall see. And VIREL changes the reduction by making the log likelihood proportional to Q omega, rather than to the trajectory reward, with the temperature replaced by the Bellman residual error. The maximum likelihood estimation chooses pi to maximize the data likelihood. Maximum a posteriori estimation adds a prior factor. Taking logs, MAP is MLE plus an additive log prior. The prior is differentiable regularizer derived from a probabilistic belief about what theta should live, where it should live before any data arrives. This constraint problem here with the expectation over f given this such that this scale is minimized and everything integrates to 1 appears with different choices of f and mu in the different algorithms. Setting the functional derivative with respect to q to 0 and eliminating lambda via normalization gives us the Boltzmann form, this q star. Plugging q star back into the Lagrangian collapses the primal into one-dimensional convex dual on eta. Once we have this closed form Q, the M step projects it back onto parametric family pi theta through forward KL. Expanding the KL and dropping the entropy term, because it does not depend on theta, gives us the weighted log likelihood. Because Q star is proportional to mu exponentiated f over eta star, the importance ratio simplifies to a softmax over exponentiated scores. Exponentiated Q in MPO, advantage in V-MPO. The Fisher information matrix of a parametric policy at theta is this here with the gradient of the log probe and then multiplied by their transpose expectation over it. A second order Taylor expansion of the KL between pi theta I and pi theta around theta I gives this scale with 1 over 2 theta minus theta I transposed times the Fisher information matrix of their difference. So a Gaussian prior on theta with precision proportional to f theta I has a log density, which to second order occur divergence in policy space. For deep network, the full Fisher is not tractable because its size is the square of the parameter count. And the decoupled KL that we see used in EM methods, such as MPO, using continuous control, are a tractable substitute for this. And it can be computed analytically, this decoupled Gaussian KL, with the policy's own mean and variance. So in this way, C mu plus C sigma. The mean and covariance terms can then be budgeted independently with two distinct epsilon mu, epsilon sigma. The mechanism then prevents entropy collapse, especially in continuous control. Finally, important sampling of policy methods estimate expectations under one distribution using samples from another. Given a target pi and a behavior b with the same support, the change of measure identity is this expectation with actions from pi of f of a being equal to expectation over a from b over pi a over b a times fa. And the ratio pi over b is the importance weight. Self-normalized importance sampling replaces the explicit normalizer with the sum of sampled weights, like we see there. And it's biased, but it has lower variance. MPO uses k-sample self-normalized importance sampling to estimate the closed form Q star. inside its step. Retrace the off-policy critic that supports MPO is a multi-step variance controlled importance corrected return estimator with per-step ratios that are capped at 1. And that lets MPO use that replay data, tens of iterations old, without a variance of this unmodified importance sampling. To derive MPO, we frame reinforcement learning as a maximum a posteriori problem on the policy parameters. A binary optimality variable O at every time step has likelihood of the probability of O being 1 given the state and action to be proportional to the exponentiated return at the state and action over alpha. So high reward actions become high likelihood ones. The MAP target is then log P of the event O equal 1 given the parameters plus log P of theta, with a Gaussian prior on theta centered at the previous parameters with precision, with Fisher precision, a prior which to second order is a Keltras region in policy space. This combined into the EM objective we see here, a function of a variational distribution Q and the policy parameters theta, optimized through coordinate ascent. The E step is a constrained variational problem, maximize expected Q under a non-parametric Q of A given S, subject to a per state Keltras region back to the current policy. Taking the functional derivative of the Lagrangian and enforcing per state normalization gives a Boltzmann reweighting in closed form, Q star, with eta star the unique minimizer of the one-dimensional convex dual, G of eta. The dual is solved per batch with a handful of Newton steps, non-neural parametric network necessary. The M-step projects Q star back onto the parametric policy by weighted maximum likelihood, with the MAP prior reappearing as a forward Keltras region. For Gaussian policies, the Kel splits additively into a mean term and a covariance term, which MPO budgets independently with two distinct epsilon mu and epsilon sigma. A permissive radius for the mean so the policy can move, and a tight one for the covariance so the exploration does not collapse, so they keep each other in check. The E step is the non-parametric optimum solved in closed form per batch. The M step is separately formulated as weighted regression with a forward Kel prior, and the two are distinct optimization problems that run alternatively. The temperature theta falls out of the convex dual instead of being chosen. The Traz region comes out of the MAP prior instead of being enforced, and the retrace of policy critic gives the Q values that drive the E step. The main cost is computational because every iteration we solve a dual, we fit a Gaussian under decoupled constraints and update a target critic. In this setup, however, we at least have coordinate ascent monotonicity guarantees such that the objective will always be either plateauing or improving in a theoretical guaranteed fashion. V-MPO retains MPO's MAP framing, but redefines the optimality variable O as a binary improvement variable I, with likelihood proportional to the exponentiated advantage rather than exponentiated Q. So the advantage is built from a non-policy n-step return minus a state value baseline V psi. So the off-policy retrace machinery and the replay buffer go away. Instead of running EM as two separate maximizations, V-MPO collapses this alternation into one Adam step over four parameter groups, the critic psi, the actor theta, and two scalar Lagrange multipliers, eta and alpha. We stop gradients enforcing that coordinate ascent block. The non-parametric E-step is replaced by a filter. The batch is sorted by advantage and the top half is dropped. And the final posterior over the surviving members here in this list of advantages is a self-normalized softmax. The filter is what keeps the softmax behaving well when advantages are mean zero. Exponentiated advantages that are negative over the full batch would flatten psi towards uniform on the worst samples and undo the improvement step. The temperature eta is not obtained by solving a batch dual. It becomes a Lagrange multiplier learned by gradient descent on a convex temperature loss. The coefficient alpha for the M step for our KL trust region from the target policy to pi theta over the batch becomes a Lagrange multiplier with a two-part loss that splits the constraint and the penalty through stop gradients. For continuous control, the M step KL splits into a mean and covariance piece, each with its own multiplier, mirroring MPO decoupled Gaussian. Now, AWR, advantage weighted regression, starts from constraint policy search instead of MAP framing. Given a sampling policy mu with discounted state distribution D, we maximize expected advantage subject to a per state KL trust region back to mu. The Lagrangian setup is the calculus of variations argument that MPO also uses, a linear objective in pi, a KL constraint, a per state functional derivative, and yields the same Boltzmann form as pi star equal the 1 over the partition functions times mu of alpha over action given state times the exponentiated advantage over beta. So the advantage is R minus V, which replaces Q. So the temperature beta acts as a mean zero quantity that we divide the advantage by, and then we exponentiate. And it's a fixed parameter rather than a per batch dual variable, this beta. There's no E step in AWR. The closed form pi star is taken to the variational target, and we go directly to the M step. Projecting pi star onto a parametric policy via for RKL is the same as a weighted log likelihood with exponentiated advantage weights. The exponentiation is taken over uniform samples from a replay buffer D rather than over the discounted state distribution D mu. Each iteration of AWR is two regressions, a value regression for the baseline and a weighted policy regression for the actor. The temperature beta stays fixed, as we said, and the buffer stays uniform. The value baseline is fit by TD lambda regression. AWR is an alternation between value regression and policy regression with exponentiated advantage weights built from supervised learning. The same Lagrangian and projection approach that produced MPO's closed form Q star produces AWR's closed form pi star. DAR specializes AWR for online language model alignment with AI-generated scalar rewards and adds a second KL constraint against a static reference policy, which resets at every iteration. Alpha in the objective controls the trust in the reference, the supervised fine-tuned model that initializes training. And beta gives an on-policy stability against the current policy. RLHF would be derived by setting beta to 0. AWR, which that is based on, can be obtained by setting alpha to 0. Solving the Lagrangian under both KL constraints gives an optimum that interpolates the two reference distributions before tilting by reward. The exponent alpha over alpha plus beta sets how much we trust the reference, and beta over alpha plus beta sets how on policy we are. Alpha plus beta acts as a unified temperature on the advantage. The two AWR type weights factor out cleanly into a regularization weight and an advantage weight. The M step is weighted supervised fine tune on K rollouts per prompt. We compute a Monte Carlo baseline from the rollouts. We normalize the advantages across the batch for stability, clip the product weight, and run gradient ascent on the weighted log likelihood, with the advantage estimate being this with the K rollouts. The EM is distilled to a closed form geometric mean tilt computed in a single line, plus a weighted SFT loss with clipped weights and per batch advantage normalization. Both alpha and beta are temperature hyperparameters. ReST-EM applies the control as inference reduction to language model self-improvement with optimality defined at the sequence level. A binary optimality variable O has likelihood proportional to a non-decreasing function of the sequence level reward. So high reward response becomes a high likelihood one, just like in the other ones. The MAP target is the low probability of optimality, conditional on the prompt. As we see here, again, with this O equal 1 comes back. The sum runs over all possible response sequences and is combinatorial computational in both vocabulary and sequence length, so intractable. So we introduce a variational distribution Q and apply Jensen's inequality to recover the elbow. Same things we saw in the other methods, except applied over response strings rather than action samples. Setting the functional derivative of the elbow with respect to Q to 0 gives the Boltzmann closed form we derive from MPO and AWR, a reward tilted current policy. Under binary correctness reward, does the match do all the unit tests pass as being the checks of correctness? The exponential factor takes only two values, one being on correct samples and x of the -1 over t on incorrect ones. Any t value that's between 0 or 1 produces the same Haar filter. The soft reweighting that MPO computes through a one-dimensional convex dual becomes a binary keep or dropped. The M-step substitutes Q star back into the elbow to give a reward-weighted log likelihood. And under binary weights, it reduces to plain supervised fine-tuning to the filtered dataset. ReST-M is a closed-form binary filter for the E-step and plain SFT for the M-step. Every iteration reinitializes the learner from the base pre-trained theta, instead of continuing from previous iteration checkpoint. Training from theta on the latest filtered dataset lets the data improve across iterations. Because the sampling policy pi theta t improves without letting the optimization trajectory accumulate the drift that would otherwise compound from repeatedly fine-tuning on a narrow filter. Monotonicity holds approximately, finite n capped per prompt selections, and SGD on the M-step replace the argmax, but the empirical curves stay close to monotone across the first few iterations from their testing. Finally, VIREL reframes things as variational inference, where the inference object is the parameterized action value Q omega itself. The Bell-Bem residual error is defined as epsilon omega, and Boltzmann policy is built with the residual error as its temperature, this pi omega action given state. The temperature is no longer a hyperparameter or a dual variable. It emerges from the optimization gap, while for epsilon omega, while Q omega is far from its Bellman fixed point, epsilon omega is large and pi omega is broad. As Q omega converges, epsilon omega shrinks and pi omega sharpens on the graded distribution. Exploration becomes transient byproduct of the critic's uncertainty, which lets the framework target the standard objective rather than an entropy regularized Merle surrogate. Introducing a variational policy pi theta with state distribution D, the elbow is this loss of omega and theta, which rearranges into a log partition minus a reverse scale minus a state entropy term that we have here. Maximizing the loss over theta is mode seeking, the same KL direction MPO and AWR use. Maximizing it over omega drives epsilon omega to 0, which tightens the bound and is, by construction, policy evaluation. The actor and critic updates are the E-step and the M-step of variational expectation maximization with adaptive prefactors that cancel the 1 over epsilon omega. Blow up the Boltzmann that also blows up the Boltzmann form would otherwise create as the critic converges. The actor reduces to reinforce style update against Q omega with an entropy bonus weighted by epsilon omega, and the critic moves Q omega towards the Bellman fixed point. Both the variational distribution and the model parameters evolve, and the temperature is part of the model itself. Replacing the uniform action prior with one that factorizes through a null policy, pi psi, converts the entropy term in the elbow into a forward KL to pi psi. And we see here the MPO loss. The psi update of the pi psi becoming pi theta k plus 1 recovers MPO's trust region structure. VIREL is variational AM with the temperature learned through the Bellman residual, the prior left as a design choice, and the inference object moved from the action distribution onto the parameterized action value function. The framework targets the standard objective rather than an entropy regularized surrogate, with the exploration schedule coming as a transient product of the critics optimization step. So all in all, EM can be seen as a skeleton for the derivations, for these derivations, which sets the scene for a structure that alternates between an inference distribution and a model. Project by KL, weight by reward, but does not fix how each of these parts are implemented. The flexibility allows us to derive MPO's full Lagrangian and dual coordinate ascent loop on one side and REST EM's filter then SFT on the other. EM remains the abstraction because what it enforces structurally is fairly small, a decomposition into two halves and an inequality on a log of an expectation with configurable dual, prior, multiplier, temperature, schedule, and trust region controls.